Hi, welcome everyone. This is the start of a new course named Foundations for Machine Learning. My name is Dr. Sridhar Panat. I graduated with my PhD from MIT in 2022. And before that, I finished my bachelor's in 2017 from IIT Madras. So all of my formal education in bachelor's as well as during PhD was in the mechanical engineering department. I took my first proper machine learning course somewhere around 2019 or 2020. It was an advanced ML course, graduate level course at MIT. And that really exposed me to many ideas that I could incorporate into my research. And after that, I used certain frameworks within machine learning called scientific machine learning, image classification using neural networks, etc., into some of my research problem statements, which was very fascinating. And when I attended those courses, I really noticed a difference between the way machine learning courses were taught elsewhere versus how it was taught at some of these best universities in the world. There is a lot of emphasis on foundational knowledge. So what I mean by that is there is a lot of emphasis on mathematics behind machine learning. There is a lot of emphasis on calculus, probability, linear algebra. There is also a lot of emphasis on coding everything from scratch. And if you compare this with many online courses out there, what those courses are trying to do is to give you some kind of hands-on experience by making you work on some toy Kaggle projects or some other projects, so that you will get a feel that you are able to build machine learning models and run them yourself. But at the end of the day, when you look back, you will not be able to explain things to someone else, which is really the test for whether you know something deeply or not. Something I have seen, if you ask someone a simple question, someone who has been learning machine learning, you ask them a simple question: why do you need activation functions in a neural network? What happens if you don't have an activation function? You just check this with many people. You'll be surprised to know that most people will not be able to answer this question. It's a very simple, intuitive thought process to understand. In the absence of activation functions, what can happen to a neural network? It will simply be a linear transformation. But to think about that from a really conceptual standpoint, you really need deep understanding of how neural networks work, what exactly is happening, how is all of this connected to linear algebra, what is the basic calculus that you need to know, etc. So this course has only one purpose. It is to teach you the very foundations that are required to advance your machine learning career. You may be interested in academia, you may be interested in industry. Currently, you may be a student, or you may be already an industry professional, whatever it may be. I'll assume nothing. I'll start everything from scratch. You will find it very easy oftentimes, but we will also move into certain advanced concepts towards the end of the course. So now let us think about the question of what exactly do we mean by foundations for machine learning? I have divided this into 5 pillars. So this overleaf document I have compiled to kind of show you the table of contents that I am planning for the rest of this course. Some topics or subtopics I might change as I seem fit as I progress in the course, but the foundations will remain the same. So I have divided into 5 pillars. So the first pillar, module 1, will be about mathematics. So I'll lay the mathematics foundations. I'll come to the details of this, exactly how many lectures I'm planning, etc., in a minute. The second module is on programming foundations. So if you do not have any programming background, if you have no idea of using Python, don't worry, we will cover a bunch of those things in this course. You might have heard of a lot of terms like NumPy, Pandas, all of these things you might have heard from people. Maybe you have experienced yourself, but we'll be covering all of that also in detail in this course. The third foundation is optimization. This is very, very important. Most often when you are actually implementing machine learning models, you will be spending a lot of time on optimization. Your model will not converge. You will face a lot of issues. But if you exactly know how these optimizers work, it will help you tremendously to rationalize your choice of optimizer or rationalize your choice of certain hyperparameters. If you don't understand these terms, don't worry at all. I don't intend to make you intimidated right now. The fourth module, we plan to cover a little bit of what exactly is happening in AI today, and what do you think, or what can you expect in the next 5-6 years. The reason why we wanted to create this module along with the foundations course is because in 2012, when people were working on machine learning, there was a tremendous focus on convolutional neural networks. But now it is slowly moving away to give way to maybe large language models in terms of popularity. What I'm saying, not in terms of applications. Of course, CNNs have huge applications even today. But there are many concepts in machine learning that are becoming exceptionally popular and probably will continue to be very useful to know and learn from a job standpoint or academics standpoint in the next coming years. So we'll be covering that in this module. So we will first give an overview of ML and DL up until this point, the supervised learning. We will also talk about generative AI. In this, we will not be covering in depth everything about large language models because that will make the course so big. So I don't intend to do that. But rather, we'll cover how the generative AI itself came into place. What were the first models that people built, and how was the results, and how can you learn that from scratch? So we'll be covering those in the module 4, and then the last module will be about storytelling and visualization. This is one of the most important skills you should have as a data scientist or ML engineer. Most of the real life data that you will get will not be clean. The Kaggle data sets that you may find will be cleaned by someone. So someone might have hosted that clean, pampered data in Kaggle or Hugging Face. You will be able to directly download it, use it. There may not be duplicates in the data. There may not be rows that are empty. A lot of things you don't have to think about in the data sets that are readily available from internet. However, when you are actually working on problem statements in machine learning, or let's say someone is testing you on your machine learning knowledge. For example, if we were hiring for Vizuara and we were to conduct a test, we'll obviously not be giving a clean data set. We'll be giving, very raw data, which is supposed to be cleaned by the candidate themselves. So it's a very important skill that you have to learn if you are going to seriously enter into machine learning. And finally, we'll be covering data visualization. And needless to say, if you can't visualize your data, you can't communicate what you have done to anyone. And visualization is through which most people will get a very intuitive understanding of what their data set looks like, what they are supposed to do, what models they could try, why are they getting very good training accuracy but very bad test accuracy. Maybe it's because of the bias in the data set. So many things like this can be understood from data visualization. So we'll be covering that also. Now let me show you roughly the kind of split that I'm planning for the course. So this foundations for machine learning, as I said, it's split into 5, right? So totally, I'm planning around 42 hours worth of content. You might be surprised why 42, why not 40? I mean, when I entered the hours, it just turned out to be this much. It could be 40, it could be 45. There is, of course, a chance for plus or minus 1 or 2 hours here and there. And typically, each lecture will be anywhere between 30 minutes to 1 hour, maybe. So I'm thinking roughly there might be 60 lectures. Every lecture won't be 1 hour, so there won't be like exactly 42 lectures, but roughly 60 lectures. It can go here or there depending on how the course progresses. So the module 1, which is mathematics foundations, alone will be 11 to 12 hours, and I have split that into 3. So first we'll be covering linear algebra with a special emphasis on vectors. Most of the operations that are happening in machine learning, you will see that it's a linear transformation. And if you can really understand the transformation of vectors, for example, from a 3-dimensional space into 2-dimensional space or within the same space, it will make so many things easy. I have personally realized the importance of linear algebra, especially while learning large language models. Of course, while learning machine learning also it's important, but if you look at some of the LLMs with huge number of parameters and multiple operations happening in parallel in multiple heads, if you have a really good understanding of matrix multiplication, linear algebra, transformations, etc., you will have a much easier time understanding many things down the road. So we'll be covering linear algebra, but not like a traditional linear algebra course, in which you will most likely get distracted or derailed because you will find it exceptionally difficult to calculate rank and many things. I don't want to make the course aligned towards a completely mathematical version of linear algebra, but rather I want to make it aligned towards what is useful for machine learning. So this will be roughly 4 hours of content, which means it could be 6 lectures or 4 lectures itself, depending on how I record. The second topic which I cover within the mathematics foundation is probability and statistics. There is softmax function, which is very commonly used in machine learning. You often have to provide a confidence level when you are making predictions. There are naive Bayesian classifiers, and there are many other models in which probability plays probably the most important role. Even in the recent Nobel Prize winning work by Geoffrey Hinton, he proposed a probabilistic approach to the Hofstede's networks, which also, Professor Hofstede also won a Nobel Prize, and his work was modified by a probabilistic component by Professor Geoffrey Hinton, and you will keep on seeing the occurrence of probability and statistics throughout machine learning. The third subconcept will be calculus, and within that, primarily differentiation. Of course, integrals are also very important, no doubt. But here we won't be teaching you about so many, theorems and proofs, and there are so many different rules for differentiation, so many different rules for integration, which is how traditionally calculus is taught. But here, we are not going to cover that, and of course we can't cover that in 3 to 4 hours, but I'm planning roughly 3 hours. This could become 4 hours also, to teach you some of the very basics of calculus, which will help you tremendously in machine learning, especially things like chain rule, partial derivatives, then several other theorems that will help you in creating the equation for backpropagation. So all of that we'll be covering in the calculus module, which will be the third module of the mathematics foundation. Now, the second pillar of foundations for machine learning is programming itself. These days, I have seen many people program using GPT or Cloud from Anthropic, which is very good. I myself use that. But if you don't have the fundamentals of programming, if you don't know, let's say, PyTorch, if you don't know NumPy or various other most famous libraries within Python, you don't know really what you are doing. You can get so much done with the help of large language models, but you will not be able to really solve a very difficult machine learning problem statement. So, for example, one of the ML problem statements that we recently used in a candidate interview test was not solvable using large language model. We ensured that it is not possible for someone to solve it with the help of ChatGPT. And things are moving in that direction. When companies are hiring, they will of course not be giving you very easy problem statements that you can solve in 30 seconds by copy pasting the problem into ChatGPT. That won't happen. So you have to know how to code things from scratch. And it will also give you tremendous confidence to say that you are a serious, proper machine learning engineer. So we'll be covering basics required for programming from a machine learning perspective in this particular module. I'm planning roughly 8 hours. So 8 hours means this could be 10 lectures, 12 lectures, depending on how the split occurs. So that is, not hours, lectures. Right. So this is the module 2. The first module was around 11 hours, which means this could be around 15 lectures, something like that. It depends on really how the recording goes. Then the third module is Introduction to Optimization. So you might have heard of gradient descent. Of course, if you are not living under a rock, essentially. But I don't think many people really understand what exactly is gradient descent. I don't think many people understand back propagation. I don't think people know what different optimizers are used for. What is learning rate? Um, I think what most people are doing is they are either googling it. They are either using large language models or just using some existing code base from Kaggle or some open repository from GitHub or something like that. They're reusing the code that someone else has written, but you can't solve this if you are trying to solve a problem for your own purpose. So optimization is something that you have to know if you want to become a serious machine learning engineer, and we'll be covering that in the third module, first part. I'm planning roughly 4 hours, maybe 5 to 6 lectures. So overall, this could be 10 lectures roughly. And the second part of the optimization, introduction to optimization module is various types of optimization, convex, non-convex optimization. So this is still, the table of content is subject to slight modification, because as I seem fit, if I feel like something is more important to be covered, I might probably change some of the subtopics. So please expect that. But the pillars will remain pretty much the same. I'll be covering the fundamentals of mathematics. I'll be covering programming fundamentals, optimization. Then the fourth module will be about the landscape of AI in today's world. I'll also briefly touch upon how AI looked like in 2012, because I'm very familiar about that. I knew what people were trying to do when I started my college undergrad. That was in 2012, and I was from 2012 to 2017. There was one kind of trend which I have observed in machine learning, but that has completely changed now. So people were focused a lot on neural networks, reinforcement learning. People were then slowly moving into generative networks, adversarial networks. Now a lot of people are working on vector databases, large language models, so transformers. So things are moving in a rapid pace, and it will continue to do so. But we will try to understand what would make most sense for you to learn if you were learning machine learning today, so that you learn most of the recent things that have happened, which will also help you in the coming years. So we will, of course, cover an overview of ML and DL, essentially supervised learning. And we will also talk about generative adversarial networks, variational autoencoders, large language models, little bit of transformers. But I don't want the generative AI part to become a transformer based section, because transformer is relatively recent. Even before that, we had GANs. So I really want to focus on how the idea of generative AI itself took place. But of course, I'll be talking about transformers so that you also know what is happening in that space. But at the end of this particular section, you will have a fairly good idea about the history of machine learning, what was happening 10 years ago, what is happening maybe since 5 years till now, and what may happen in the next 5 to 6 years. So that is my idea of creating this module. And this is roughly 8 hours I have planned. So another perhaps 8 to 10 lectures, depending on the length. And then the last module will be data visualization and storytelling. So storytelling using data is mostly through, showing data in the form of tables or visuals like graphs. When COVID happened, I'm sure you must have seen a lot of amazing ways in which you could visualize data, which can give insights which otherwise will be missing. At the very beginning of COVID, I saw like a data which was showing a plot of how COVID is progressing in US versus Portugal. If I remember correctly, Portugal or some European country, they had COVID initial cases detected a bit earlier than US, and they had a certain trend, certain rate at which COVID was rising, normalized by the population. And there was a very nice Medium article that explained how we should be even more cautious and even more worried if we are in the US. I was doing my PhD in the US at that time. And they had some very nice plots to kind of substantiate their argument as in, okay, currently the cases per 100,000 people in the US is not very high, but it is also deceptive for so and so reasons. And here is why. And they showed some brilliant visuals which really convince you about your need to be very careful. And I'm sure in many other occasions you must have seen the power of data visualization. This might seem like a trivial exercise for many people because, oh, what's the big deal? I just need to plot something. I just need to make a bar plot or line chart. What's the big deal? Excuse me. But it is a big deal if you really think of the idea that you might want to convince someone that what you have done is the right thing. So I have seen many companies using dashboards from. You might have heard of this platform called Streamlit. Streamlit. So this allows you to create beautiful dashboards right using like with the help of Python. You don't have to code in React or HTML. So essentially, if you have a ML model and if you want to display your results in a beautiful dashboard to your clients, you can host it on Streamlit. You can send them a Streamlit link, so they can play with it. They can see what you're working on, what you're proposing, etc. So the reason why these platforms have become so famous, I think Streamlit is a very big company. I think they are close to $1 billion in valuation, if I'm not wrong. And the reason why it has become so popular is because it makes it so easy for people like you who wish to be machine learning engineers to visualize data and tell the story to someone else. This is also important if you are writing papers. It's also important if you are working in a company, within a team, or if you have a client, which is another company to whom you want to communicate what you're proposing. So we'll talk about data itself first, data cleaning, data manipulation. If data is absent, what do people typically do? If data is biased, in the sense like if there is a lot of data in one category and less data in another category, what do people typically do? If you are getting surprisingly really good results, how can you check if your data is the issue? So one of the papers that we recently published in arXiv, which also got accepted into NeurIPS, was about identifying human versus AI written text. So we tried various fundamental ML based approaches. We also tried advanced NLP, natural language processing methods also. But one thing I particularly noticed in the beginning was when I was running the model on data which I fetched from Hugging Face, I was getting very high training and test accuracy, like 100%, close to 100% or 100% itself. Then I was like, wow, this can't be true because I have not pretty much done anything. I just used an existing NLP model. I used naive Bayesian or something, if I remember correctly. And then I was a bit, I mean, initially I was surprised, but then I got frustrated because I could not figure out a way to make the model bad. The model was giving very good accuracy. Then later, when I started looking at the data set deeply, I noticed that there are so many duplicates within the data. So although it had like 500,000 or so rows, many rows were duplicating themselves. And because of this reason, there was a huge overlap between the test data and trained data. And you can imagine why this happens. If you have 500,000 rows and if there are so many duplicates, if you randomly split this into training and testing, it's very likely that the testing data, which is a random row, will be exactly same as some row in the training data. So this was happening in my data set, and as a result, I believe I was getting very high accuracy. And then later I cleaned up the data, I deleted the duplicates, then the accuracy reduced to 95% or something. Then also I noticed that something was wrong because, okay, my model was 95% accurate, but when I was testing with actual ChatGPT generated content, the model could not predict that this was generated by AI. It was saying that this was generated by human, but that was wrong. And not only that, I copy pasted my own paper abstract, which I had written a few years ago. It was completely manually human written, and that was being predicted as 56% AI written or something like that. So then I realized that, okay, the data set in which I have downloaded is a very particular type of data set, and I need variety and quality of data. So I realized that I have to work a lot more to get very good data set, and this allowed me to focus more on building custom data sets. And then later, with the help of our team, we really nailed the problem, and we had a very good model which worked on custom data set also very, very well. So data, like dealing with data, is something that you have to know if you want to become a serious machine learning engineer, that too from a fundamental perspective. So we'll be covering all of that in this section 5.1. which I have shown here. And the last section, obviously, is data visualization. Whatever you do with data, just show it instead of talking. So this will be around 8 hours. So I know that I have so far written around this may be 10 to 12 hours. So 10 to 12 plus this is also maybe 10. So 22, let's say roughly. This could be another 10. So 32, 35. This could be 42. Sorry, 45, 47. Then another 15, 57, 60. So that's my calculation for roughly 60 lectures. But as I already mentioned, it's not very accurate. It can move here or there. But this course, rest assured, will give you the strongest possible foundation for becoming a serious machine learning engineer. And you will feel exceptionally confident after this. If someone asks, do you know what is most important for machine learning? Do you know why linear algebra, calculus, probability, why these are the fundamental mathematical tools that you have to have if you want to be a serious machine learning engineer? If someone asks this question, you should be able to answer, or you should be able to educate someone else on why these are very, very important. So that will be the course. We will start with the mathematics foundations starting from the next lecture, specifically linear algebra. And I couldn't be more excited to build this course and to teach you and also learn along the way, of course. And I hope all of you will learn something. You will follow this course throughout. I have seen a trend where people very often start a particular course, watch the first lecture, watch the second, third lecture, and then it drops down. So whenever we plot a graph of the number of people who are attending a course in terms of lecture, most attendance will be in first 2-3 lectures, then it will slowly die down. But I hope you will stick with this course, and I hope you will stay with me till the very end of the course. And I really hope you will gain the confidence that you're looking for to be a very foundation level machine learning engineer. So thank you so much and welcome to the course.